Welcome back. So we're going to spend today looking at limits with the trig functions. And there's two important rules that we want to remember when we talk about the limits with trig. And those are the limit as x goes to 0 of the sine of x over x is equal to 1. And we saw this when we looked at the numerical values or when we created the charts. Another way you can look at it is the limit as x goes to 0 of x over the sine of x equals 1. And the second one is the limit as x goes to 0 of 1 minus the cosine of x over x is going to equal 0. Likewise, the limit as x goes to 0 of the cosine of x minus 1 over x equals 0. So these are two rules that you really want to remember, and we're going to use quite a bit within this section. And what I want to do is, instead of just looking at it, both of them numerically or through that chart, I want to throw in the squeeze theorem and kind of give you an idea of how that's going to play into being able to find the limit, and we can go ahead and prove these using the squeeze theorem. So what does the squeeze theorem tell us? Well, the squeeze theorem tells us that if we have three functions, h of x, f of x, and g of x, and we know that h of x is always less than f of x, which is always less than g of x, for all values of x on an open interval that contains some value c, except possibly c itself, then if we know the limit of h of x is L and the limit as x goes to c of g of x is L, then we know the limit of f of x as x goes to c is L as well. What does that mean? Well, what I like to do is, again, look at it graphically and kind of give a picture of what this is going to look like. So let's take an h of x, and we're going to throw this in green. And maybe we have h of x there. And then we have an f of x, which is going to be larger than h of x. So it's going to have higher y values. So it doesn't matter where h of x is, as long as it's higher at some point, or equal to. So maybe it comes in like this, and then maybe just in there like that, and then comes out like that. All right, and then maybe we have our g of x, and we know g of x is, again, going to be larger than f of x, which is larger than h of x for all values. So we're going to put this one in purple, and it's going to be higher here. And then maybe this comes down and then bumps up and then comes out here as g of x. And I draw this little area, hopefully, you kind of notice this value in here, this region. We're going to call this value C. And that's very important because that's kind of our squeeze theorem. Notice we've kind of sandwiched f of x in between h and g of x. And we're bringing these two functions together at c and then going apart again. So we know the limit of each of these values. So we know that the limit as x goes to c of h of x equals some value. And that value can be found by looking at the y value there. So we call that L. We also know the limit as x goes to c of g of x. And again, as that comes in, we know that limit, those branches are coming together at L. So if we know the limit of h of x and g of x are both L at c, then we know, and again, 3 dots in a triangle means therefore. So therefore, did I spell that right? I don't know. Anyway, therefore, we know the limit as x approaches c of f of x has to equal L as well. So why is that important to us? Well, it's going to be important to us here as we look at the limit of the sine of x over x as x goes to 0. So what I've created here is a unit circle, part of a unit circle. We know the radius is 1 in both of these directions. And what I want to focus in on is the area of this sector in here. And we know the area of a sector, hopefully, from our pre-calculus days, the area is given as 1/2 r squared theta. All right, so we also know the radius of this circle is going to be 1. So the area of this we can simplify as 1/2 times 1 squared times theta, or theta over 2. And that would be the area of that region. Well, what I'm going to do is create two triangles that I know something about. To start, I'm going to create a triangle here. Well, sorry, it's going to be in here. My height is going to be in here. So what do I know about the area of this triangle? Well, I know the height, and I know my base. My base here is going to be 1. My height, in this case, well, I know that any point on the unit circle can be written as the cosine of theta, sine of theta. Hopefully remember that. X is the cosine, sine is the y. So we know the height of this triangle is the sine of theta. We also know this base is going to be 1. So the area, we're going to call this triangle 1, or triangle small if you want, is going to be the sine of theta over 2. Because we have the base, which is 1, the height, which is sine of theta, and the area of a triangle is 1/2 of the base times the height. So we have 1/2, 1 times sine of theta. And we know that that area is going to be smaller than the area of the sector. So we know the sine of theta over 2 is going to be less than or equal to this theta over 2. And this is our actual area. Well, now what I wanted to do is to bring in that squeeze theorem, we need another triangle that's going to be larger. Well, if I come over here, switch here into maybe a red marker, and I come over to this point, or to this triangle, I know, again, my base is 1. My height, in this case, is going to be y. I'm not sure, again, what that point is. We know that we have the point xy, that we're coming over and then up. We actually know it's 1y, because we're coming over 1 and up y units. All right, so what do I know? Well, if I take the tangent of this theta, I know tangent of theta equals the opposite over the adjacent, or y over 1. So I know if I multiply the 1 over, the tangent of theta is equal to y. So I know the height of this triangle is actually the tangent of theta. So if my height is the tangent of theta and I'm coming over 1 unit, or my base is 1, the area of my larger triangle, I'll call it area big, triangle big, area, is going to be 1/2 of the base, which is 1, so 1/2 times 1, times the height, which is the tangent of theta. So I have the tangent of theta over 2. We know that this is going to be larger than the area of the sector, which is also larger than the area of the smaller triangle. So I've set up my squeeze theorem. Now if I can find the value of this, find the value and the value of this, I know then the limit of this. Well, we don't necessarily have something that works like, or looks like the sine of x over x. I can replace my x's with theta, so I get sine of theta over theta, but I don't have that form. So what I can do is kind of manipulate this through algebraic reasoning. First thing I can do is go ahead and multiply each of my terms in there by 2. If I multiply each term by 2, it's not going to change my inequality. So I'm going to get the sine of theta is less than or equal to theta is less than or equal to the tangent of theta. And then what I'm going to do is I'm going to divide each of my terms by the sine of theta. And if I divide that, then I have 1 is going to be less than or equal to theta over the sine of theta, which is less than or equal to, well, if I have the tangent of theta divided by sine of theta, I can simplify that simply by taking it as sine of theta over the cosine of theta divided by the sine of theta. This is over 1. Flip and multiply. I end up with 1 over cosine of theta. From here, I can take the reciprocal of each of these pieces. The reciprocal of 1 is 1. The reciprocal of the sine of theta over theta, or theta over sine of theta, is sine of theta over theta. And the reciprocal of 1 over cosine of theta is cosine of theta. And when I do that, that changes these symbols. This becomes a greater than, and this is going to become a greater than as well. If you don't believe that, play with some numbers, take the reciprocals of them, and see what happens. All right? So say take 1/2 and 2/3. You know that 1/2 is less than 2/3. If I take the reciprocal, I have 2 and I have 3/2. So I know that 2 then is greater than 3/2. And this is going to work for any reciprocation that you do. Then what I can do is take a kind of a pancake flip, if you wish, and change these instead of being, or rewrite it, instead of being greater than symbols, I want that less than symbol. Remember, from the squeeze theorem, h of x has to be less than or equal to f of x has to be less than or equal to g of x. Well, in this case, we're greater than. But I can write this and read this as the cosine of theta is less than or equal to the sine of theta over theta is less than or equal to 1. And I can write it that way. So cosine of theta is less than or equal to the sine of theta over theta, which is less than or equal to 1. Now, if, again, we're looking for that limit of the sine of theta over theta, so if I take the limit as theta goes to 0 of the cosine of theta, I know if I plug in 0, I get the cosine of 0, which is 1. Likewise, over here, if I take the limit as theta goes to 0 of 1, well, there's no value there that's changing. It's a constant. I know I get 1. So if I know the limit of the cosine of theta equals 1, and the cosine of 1 as theta goes to 0 is 1, and I know that these two functions are sandwiching or squeezing the sine of theta over theta, then I know the limit as theta goes to 0 of the sine of theta over theta is going to equal 1 as well. And you can use this to verify the other function as well. The limit as x goes to 0 of 1 minus cosine of x over x equals 0. So what are we going to do with that? Oh, we can come back here, sorry. So remember theta, we can let theta be whatever we want. So we want it to the sine of x over x. Well, as long as this theta is the same, which they are, then we know that limit's going to be 1. So likewise, if I gave you the limit as x goes to 0 of the sine of 5x over 5x. So as long as these two values are the same, then we know that limit overall is going to be 1. And that's going to be very important as we go forward and look at example 1 here. We're looking at example 1 being the limit as x goes to 0 of the sine of 7x over 3x. Notice here, these two values are not the same. But we can look at this in a lot of different forms. One, we can take and think of the top as being 1 times the sine of 7x over 3x. So we could really write this as the limit as x goes to 0 of 1/3 times the sine of 7x over x. And that 1/3 multiplied by that, 1/3 is a constant. It's a scalar multiplying. So we can bring that to the front of this limit. So we have 1/3 the limit as x goes to 0 of the sine of 7x over x. Now what we can do, remember I want these two values to be the same. So if I multiply by 7 over 7, It's not going to change my limit because 7 divided by 7 is still 1. What I can do, though, is look at this. Again, this 7 is in the numerator, the 7 denominator. I can think of this. I'm going to go ahead and write it to show you. So we have 7 sines of 7x over 7x. Again, this 7 is a scalar multiplying, so we could bring this 7 out. We could bring this 7 out as well, but we don't want to because notice now we have the sine of 7x over 7x. So I have 7/3, the limit as x goes to 0 of the sine of 7x over 7x. We know by definition this piece. We know that that limit is 1. So I have 7/3 times 1, or 7/3. And that's going to be our limit. If I look at the limit as x goes to 0, x goes to pi of sine of x over x, we have to be careful, and we got to remember, I probably should have done it up here as well. Remember, the first rule of limits is the plug and chug. So if I plug in 0 up here, I would have ended up with sine of 0 over 0. Sine of 0 is 0 over 0, which is indeterminate. So that tells us that we got to do something with it. That's why we did what I did down here. In example 2, that's why I backtracked, because when we take x going to pi, well, the first thing we're going to do is plug in that pi. So that's going to give us the sine of pi over pi. Well, what do I know about the sine of pi? The sine of pi, again, is 0 over pi, and 0 divided by pi is 0. So that gives us that value. Now, what would have happened if we went to the limit as x goes to pi over 2 of the sine of x over x? Well, in this case, I take the sine of pi over 2 over pi over 2 by plugging in. Sine of pi over 2 is 1 divided by pi over 2. Multiplied by the reciprocal, I end up with 2 over pi. So notice, we don't get just that 0 or that 1 value with this. So we got to be very careful to make sure we plug and chug first before we just assume that we're going to do some fancy footwork there. I have just 2 more examples. I know this is kind of a longer set that we're going today. We're going to spend a couple days on this, so there won't be necessarily a big set tomorrow. If I look at the limit as x goes to 0 of x cotangent of x, again, if I plug in 0, I get 0 times the cotangent of 0. The cotangent of 0 is the cosine of 0 over the sine of 0. And we have 0 times that. Well, what's the cosine of 0 divided by sine of 0? Cosine of 0, remember, is 1. The sine of 0 is 0. So I have 0 times 1 over 0. Remember, we can't divide by 0. So this is, again, an indeterminate form. So what can I do with this? Well, I'm going to go ahead and break up my cotangent of x into the cosine of x over the sine of x. Now, by definition, we can break this up. We can break this into the limit as x goes to 0 of x over the sine of x times the limit as x goes to 0 of the cosine of x. And I chose to do x over sine of x for the simple reason from the very first page of notes there, where I gave you, by definition, the limit as x goes to 0 of x over sine of x is equal to 1. So anytime I can get to one of those forms, it's going to make my life a lot easier. So I know this is going to give me 1. The limit as x goes to 0 of the cosine of x. Well, I know if x goes to 0, I'm looking at the cosine of 0, and the cosine of 0 is 1. So I have 1 times 1, or 1. Finally, I have example 4. I have the cosine of x minus 1 over the sine of x. And that looks hopefully, again, familiar to us, that cosine of x minus 1. If this was divided by x, then I would know that limit. And if I had an x over the sine of x, I would know that limit as well. So what I can do, again, is arbitrarily multiply by x divided by x. And if I divide by x, I'm still multiplying it by 1. And I'm not changing the actual meaning of the function, I'm just changing what it looks like. So what I'm going to do is I'm going to break this into two functions, or two limits. I'm going to take my x over my sine of x, and to that I'm going to multiply by the limit, as x goes to 0, of the cosine of x minus 1 over x. Because I know this limit by definition, I know this limit by definition. This limit here is going to be 1. This limit over here by definition is 0. And 1 times 0 gives me 0. So I know that was a lot to take in. I'm going to spend a couple of days with the limits here with trig, and we'll see how we do.